Hello, everyone. It's time to prepare for another week of lab. So this week we are going to be having a little bit of fun. We're going to be extracting caffeine from tea. So basic premise this week is we're going to start by making a big old cup of tea that you would never want to drink because it's going to be full of all sorts of fun organic stuff. So from this giant bag of tea we're going to make, our goal this week is going to be making a crude caffeine extract. So what we're going to be doing is we'll dissolve the caffeine into tea, and then we're going to extract that caffeine from the water by dissolving it into various other phases. And again, removing all of the extras, leaving behind just a nice impure composition of tea. It'll have some residue from the process. So next week, we're going to go ahead and try and purify this crude extract, first by performing recrystallization, so essentially dissolving it and crystallizing it slower, and then doing a sublimation where we can take advantage of the fact that you can evaporate caffeine and solidify it right out of the gas phase. And when we do that, once we have our impure and pure products, we're going to evaluate the relative purity using our good old friend TLC and bring back melting points from Gen Chem. So let's dive into what we're doing this week. How are we going to do this extract? So we're going to be extracting caffeine by adding a series of different phases. So each time I add a phase, we're going to go ahead and find that some component of our mixture is going to prefer one phase over the other. Solid over liquid, organic over aqueous. So what we're going to do is try and collect that desired phase, and then we're going to treat it again to remove any impurities that came along with. Now, one of the very fun things whenever we're doing one of these separations is that it's always possible to diagram exactly where every component of our mixture is located based on our knowledge of things such as solubilities. And we can do this using what's called a SEP scheme. So the major idea in a SEP scheme is you will model every time you add a phase or do some sort of operation on your mixture. And then if I add a phase, typically we're going to end up seeing things separate out. Liquid solid, gas liquid, gas solid, so on and so forth. And then what we're going to do is identify what component should be present in each phase. So who's running along with A and who's running along with B. So this is kind of general. So let's look at a specific example to demonstrate how we'll do this for caffeine. So let's say I've got a mixture of benzoic acid and anthracene. So both of these are going to be relatively nonpolar species. So we'd expect them to both be soluble in organic conditions. But what I can go ahead and do is go ahead and dissolve the system in dichloromethane, at which point the anthracene should be readily soluble. But I'm going to mix in a little bit of sodium hydroxide and water. What that sodium hydroxide is going to do is it's going to see that benzoic acid. And while benzoic acid only has one polar group for a big 7-carbon chain, we'd expect this to be mildly soluble in water, but very soluble in organics. But when I treat it with sodium hydroxide, that sodium hydroxide can remove a proton from the benzoic acid to make something called sodium benzoate. This is an ionic compound, and it will be very soluble in water, as almost all ionic compounds are. So at this point, what I should do is I should find my aqueous phase will contain that sodium benzoate and water, while my organic phase should contain that dichloromethane as my solvent and anthracene as my major component that I was able to pull out of this mixture. So I was able to separate these two various species. Now, one of the things you should pay attention to is making sure to note any minor traces of the other solution. If I'm going to mix water and dichloromethane, I'm always going to get a little bit of dichloromethane in my water, and I might have not entirely reacted any of that sodium hydroxide I have left. So I'll have a little bit of excess sodium hydroxide and some mild trace dichloromethane. On the other side, water is really pernicious and it will get into all kinds of things. So I might see a little bit of trace water left in my organic phase. And so at this point, if I wanted to have pure anthracene or sodium benzoate, I'd have to remove those trace contaminants. So let's go ahead and see how this applies to what we're doing today with caffeine. I'm going to give you the general framework. I want you to go ahead and try and fill it in. The filled in phase diagram will really be what to do next week as kind of a take home tracking to see you to make sure you were able to follow what we're doing at every step. So we're going to go ahead and start by taking our solid tea and placing it into hot boiling water. It's going to contain a little bit of the calcium carbonate. So that calcium carbonate is going to play two major roles. So first thing it's going to do is it's going to help accelerate that breakdown of those tea leaves, and it will help encourage caffeine from leaching out of the solution. But it turns out that there's also going to be any number of semipolar substances like gallic acid. So gallic acid will be, again, as you might see, semipolar. It might be able to dissolve in a semipolar, slightly polar, slightly polar mixture that we'd be extracting our caffeine to. But it will definitely go into our aqueous phase. But one of the cool things that we're going to end up finding is by adding that calcium carbonate is going to be a mild base. So it can deprotonate our gallic acid, which is going to become really important for the next stage, as it will render it from a slightly polar to an ionic compound. Now, what we can do is any of our extra tea solids left behind should go into our solid phase, along with some excess water. So we're going to go ahead and strain out these solids using our watch glass to remove any extra solids, the same way you would go ahead and strain pasta using the lid of your pot. So what we're going to do is then take this aqueous tea extracts I've collected, and I'm going to go ahead and combine it with a little bit of dichloromethane in a separatory funnel. So really what a separatory funnel is it is a nice glass container with a stopcock at the end that I can go ahead and mix multiple different components into. And what should happen is that these two components should separate, as long as they are not miscible, such as dichloromethane and water, they should separate based on density. Our heavier component should sink to the bottom. Our lighter component should rise to the top. So think really tightly, who do you expect to be heavier? A solution containing chlorine or water? So what we're going to do is we're going to go ahead and try and extract our organic phase. So we're going to go ahead and try and pull out our dichloromethane. As it turns out that we would expect our caffeine to be soluble in the organic phase, well, any of those semipolar acidic compounds, such as gallic acid, now that they are formed ionic compounds, should mostly go into the aqueous phase. Now, when we do this, I will have a nice organic phase that I can go ahead and collect. This is going to include some excess water that essentially would have leached into my organic phase. Because even though I can use the separatory funnel to make a pretty fine line in between my organic and aqueous phase, a little bit of water will always kind of seep through. Entropy is like that. So we can go ahead and remove that extra solid using something like magnesium sulfate. So magnesium sulfate is a hygroscopic material that will readily absorb water. And so it should go ahead and readily absorb water, but still remain as a solid. I can then go ahead and remove this solid hydrate using something called fan-folded fluted filter paper, which is just a fancy way of saying origami with filter paper that will maximize the surface area and encourage quick filtering of our organic phase. So I can remove all that extra hydrated magnesium solid, and the only thing left behind should be my nice organic phase. Then I will have this organic phase that I can go ahead and evaporate out using a rotovap. So a rotovap is essentially just a fancy piece of equipment that's been sitting in the corner of the lab all semester that will go ahead and apply heat to your solution, which will make it more likely to evaporate, and then a vacuum that will remove any vapor as it forms. So in about 5 to 10 minutes, you should have just a small amount of residue left behind that will be rich in our that will be uh, rich in our caffeine and comparatively uh, poor in our liquid. So before we go ahead and start lab, I'm going to want you to do a couple things. If you have it, please go ahead and look over Morrig chapters 9 over how to do filtrations. Chapter 10, walking through these extractions. It is worth noting we also have a diagram of these separation schemes as Appendix 4 in your lab manual on Canvas. And then chapter 11 talking about the use of drying agents. Then make sure to go ahead and read the lab manual for experiment 4. You should already be watching this video, so that's great. Now, each of those steps of the procedure that I walk through has a separate video for it. So there is a video on Canvas of how you can make your own folded filter, how to fold your own filter paper. Another video on how to use a separatory funnel to perform a liquid-liquid extraction. And a third video on how to use the rotovap. I'll probably mostly be using the rotovap due to time constraints, but it's good to have a background of what a rotovap is and how it works. Then before Tuesday, make sure to go ahead and complete the Canvas pre-lab quiz, write your pre-lab notebook, answer any of the questions to be considered, and go ahead and make sure to complete that separation scheme worksheet that I handed out last week and turn it in at the beginning of class. Now, once we're in lab, we're going to go ahead and do our usual meet in the chem lounge. I'm going to go ahead and give a safety overview. And this is probably one of the more safety concerning labs we have this semester. Once we get in, immediately start to set up your tea mixture to boil. Again, once it's boiling, go ahead and make sure to simmer for 10 minutes. That 10 minutes is once it has started to boil, just like when you're working with pasta. Now, while that's boiling, there's many extra steps you can do. Like you can fold your fluted filter paper. You can make sure to pre-weigh and label on your flask. You can make sure that essentially all the next steps go faster. Once you have your nice mixture, you can go ahead and decant that liquid using your glass. You're going to decant this into a beaker. And again, perform 2 to 3 small rinses, as we don't want to have too much of our tea mixture, so we leave enough room in our separatory funnel. Now, in that beaker, you're going to need to make sure to let that solution cool to near room temperature. Once it's essentially, you can touch the glass, then you're going to want to place it into an ice bath to cool it down further, because we want this to be nice and true room temperature or straight up cold before we place it in the separatory funnel, as the separatory funnel is a confined container, and you never want to have a hot liquid in a closed system. Now, we're going to go ahead and extract the solution with our dichloromethane. We're going to do this with 3 sequential extractions, each with 20 milliliters. So we're going to do this 3 separate times, and make sure you place this into a clean, dry flask so there's no extra water in the system. Then, once you've collected your 60 milliliters of dichloromethane, we're going to add that magnesium sulfate to remove the excess water. You can always tell if you've added too much or too little magnesium sulfate, as it should change texture when it interacts with the water. So it should become clumpy. If it stays a nice light powder, it means it didn't absorb water, and you should have a dry solution. Then you're going to want to go ahead and gravity filter your sample directly into a dry round bottom flask. Then you're going to cork that flask and bring it over to me so I can go ahead and rotovap it down. Once I've returned it back to you, you're going to want to place that sample into a pre-weighed, labeled 25 milliliter Erlenmeyer. So we're doing this in an Erlenmeyer because we're going to be placing it in the back of the hood so it can continue to evaporate over the next week, which is also the reason you want to make sure it's well labeled and out of the way so the other groups don't end up knocking it over. Then you're going to go ahead and make sure that everything is nice and clean. So a couple things to keep in mind when you're performing the lab. Always make sure coming in know exactly how much of each reagent you need and pay attention to how accurate these numbers need to be. If it says approximately 8 grams, it does not need to be 8.00. Again, approximate is good enough, but whatever you weighed out, make sure you record that. And again, especially because we're using a lot of hot glass, make sure you do not place any of the hot glass directly onto a cold surface. If it does, it can crack your glass, and that's not good for anybody. Similarly, make sure that tea extract is cool before you place in the separatory funnel. If it isn't, it can essentially produce too much vapor, and that will cause some issues in your separation. Now, this one's really important. Soon as we start handling dichloromethane, the gloves should come out and you should continue to use them. Dichloromethane is fairly toxic, and I'll give some specific recommendations once we're in class. Now, when you're separating your organic and aqueous fraction, try to avoid incorporating as much water in avoid incorporating any water into your organic fraction. So if you have to choose about getting all of your organic fraction or including any water, always avoid including any water. Now, when you're removing that water residue, again, be careful that water is going to float on top of your organic solution. So if you're trying to make sure that magnesium sulfate comes in contact with your aqueous, you might need to mix it up a little bit more. And again, alternatively, you can try and make sure to shake any magnesium sulfate to directly on top of any water beads you see floating. Then again, at the end of the lab, do make sure that product flask is uncovered because we need that last remaining dichloromethane to evaporate by next week. And again, make sure it's not in your drawer as it as the remaining residue can cause issues, and you want it in the well-ventilated hood instead. Now, the last final thing to keep in mind is that the waste, we have a separate waste container for our organic waste and our aqueous waste. Whenever you're working with something, pay very close attention. Am I using my dichloromethane, or is this mostly aqueous? All right, so once you're done with lab, make sure you go ahead and complete your post-lab scans. I will also be handing out a Caffiene SEP scheme. So you're going to want to go ahead and complete that when you're done with lab. If you do it quickly after, you'll probably have everything fresh in mind. And I'm going to try and grade your other SEP scheme by the end of lab so you will have some feedback to use. Then don't forget, I gave an extended deadline on that PyMol lab. So make sure you have, make sure to work on that PyMol lab and don't put it off till the last minute. That should be everything. And otherwise, have a good weekend and see you in lab.